Azin Asgarian is currently an applied scientist at Georgian Partners R&D team, where she works with companies to help adopt applied research techniques to overcome business challenges. Azin holds a master's in computer science from the University of Toronto and a bachelor's of computer science from the University of Tehran. Azin also has an extensive publication background working on topics ranging from algorithmic bias in computer vision, workplace injury prediction, and transfer learning. As for Franziska Kirschner, she was born a physicist and completed an undergrad and her PhD in physics at Oxford. During her PhD, she focused on both the theoretical and experimental aspects of superconductors and magnetic monopoles. And as is the fate of all physics PhDs, she eventually defected to the machine learning community after completing her PhD. And now she's a senior deep learning researcher at Tractable.ai, applying cutting-edge computer vision algorithms to the insurance industry. Tractable's algorithms perform visual damage assessment for vehicles in disaster zones, accelerating the claims process. And Tractable is also ranked 5th on InsurTech list of top 100 companies in the insurance technology space. So without further delay, yeah, please.
Cool. Thank you very much for that introduction. Yeah, we're going to talk a little bit about Tractable today and how we're overcoming something called the cold start problem. But let me start off by telling a quick story. So I woke up this morning, kind of somewhat unsurprisingly, I guess, unless I'm very good at sleepwalking. And I kind of poked my head out of the covers, good to go. And then I was greeted by a nice sort of like crisp 5 degrees in the air. I realized I'm mainly talking to an audience of, like, I guess people based in Canada. So maybe me whining about the British winter is probably just a bit dense in comparison, but it was very cold. That's the main thing. And then I kind of put my head back in the duvet and decided very probably not to continue with this path of action for the foreseeable future. But I guess like everybody who has to get up in the morning, eventually I kind of had to drag myself out of bed. In the same way that dogs look like their owners, AI thinks a lot like its machine learning researcher who trained it. And so just like me, the AI often has to deal with these problems for a cold start. And just like me, it also has to overcome it if it's going to kind of work in the real world. So we're going to tell you a little bit about how we did that today. So quick outline, you're probably wondering who we are. I was going to say we're probably wondering who we are, but actually Ali gave such a good introduction, you're probably good for that information, but I'll talk about us anyway. And then I'll talk a bit about why we care about this cold start problem in machine learning, how we then overcame it, and then what was the business impact, and how has that allowed Tractable to be the startup that it is now. So firstly, who are we? We're a team of researchers from Georgian Partners, a VC firm based in Toronto, and Tractable, a startup based in the UK. You should hopefully be able to identify who we are out of the speakers. If you can't, you probably need some more training data, but that's fine, we can sort you out.
Thank you, Franziska. Hi, everyone. Thanks for joining us today. I'm Azin Asgarian, as Ali introduced me. Thank you, Ali, for the introduction as well. So in Georgian, we invest in the best growth stage AI companies like Tractable. This includes using data and AI to identify the best companies for investment, as well as helping our portfolio companies and supporting them the post-investment. And an example of that is basically we're recently building a platform to help our portfolio companies solve challenges for scaling. So now you may be wondering why an investment company need an R&D team for, which I think is an excellent question. So in summary, the R&D team of Georgian help with driving product differentiation, and we do this by basically working on 4 different areas. So Franziska, if you go to the next slide. Thank you. Yes. So we work on 4 different areas to actually achieve these. The first area is identifying the disruptive the market. The second area is that we help our portfolio companies with finding and recruiting the best talents on the market. We understand the impact on the business software models, and lastly, we help our portfolio companies with adopting the technology. And in order to do that, we basically do different types of collaboration with our portfolio companies, such as deep engagement, hackathons, advisory projects, and so on and so forth. So these, basically, the results of these collaborations are either reusable toolkits or research papers, which I have shared like 2 QR codes at the end of this page. If you're interested to learn more about what we do at Georgian, you can check them. And as I mentioned earlier, Tractable is one of our best AI companies, and what you'll see through the rest of this talk is basically the result of our collaboration with Franziska and her team. So with having said that, I'll pass it to Franziska to talk about Tractable's mission and what's the problem that they have been trying to solve in the
Cool, thank you, Azin. Yeah, so Tractable is an AI company that uses computer vision to automate accident and disaster recovery. It's actually Tractable's 6th birthday today, which is really nice. And it's just, I guess it's like a child prodigy because it's already won a ton of awards. It's managed to get $55 million in funding, thanks to the many VCs, including Georgian. So I guess thank you, Azin, the team, for keeping me in my job. And we have a team of 140 all across the world. We have a very strong R&D team, and it is a really awesome place to work. So we have a product. So you crash your car into your favorite friend or enemy. You take some photos of it. Make sure you get a nice selection of photos all around the car so you can see the damage. Then you can submit those photos on our app. Even if you thought you did a good job, sometimes you haven't, but we'll tell you, so then you can submit a few more. Once you've added your additional photos, all of that goes into our app, and that goes to our AI. Our AI will then look over all of those images. It will see what parts are in those images, which ones are damaged, and what does it need to do in order to repair those damaged parts. And in the end, out comes probably the first ever full repair estimate written by an artificial intelligence in the world, which is really cool. But to get to this place, there are a lot of challenges we need to overcome. So one thing is this cold start problem. So Tractable takes some images plus some metadata, for example, like where was your car driven into? That goes through our AI, and out comes the repair estimate, which kind of looks kind of easy when you draw it in a nice flowchart, but you've got to trust me, it's not easy. We're in 13 countries in 3 continents all around the world, but as the title probably suggests, more customers, more problems. Cars around the world all look very different. If you have an AI that is brilliant with American cars in the US, it will have never ever seen a K car in Japan before. And so it really struggles with those new cars. Not only do they look different, they are also repaired differently. And so Americans, they really like to kind of repair parts. Other parts of the world, they love to replace parts. Even the tiniest scratch, they're like, oh, just throw it away. We'll get a new one. So this is difficult, but it's even more difficult because different people around the world will repair cars differently. It's physically exactly the same damage. You can drive your car into something in Mexico. It will be repaired in one way. You can have physically exactly the same accident in Thailand, and it will be repaired a different way. So we have different shifts in our data that we need to deal with. So kind of as a result, if we have a model that performs really, really well in one country, we fly it around the world, suddenly it's got this cold start problem because it hasn't seen any data from the new country. And so it ends up doing really badly. They flip the tables, and it's a nightmare. So you imagine the way to come around this, you've got a lot of data from country A. Why don't we just collect some more data from country B? But this deep learning, it is computer vision. So more data mainly means more money and more time spent collecting that data, which makes it a very difficult problem to scale your product globally. So what we need to do is we need to find a way to adapt to all of these different shifts all around the world quickly and in a data efficient manner. And that is how we are overcoming the cold start problem in Tractable. So Azin's going to talk a little bit about how we are in detail going to solve this problem.
Thank you, Franziska. So yeah, Franziska talked about what the cold start problem is, but in the next few slides, I'll talk about how we're gonna overcome it and how we basically made some improvement in our project. So as human beings, we're really good at transferring our knowledge. When we encounter a new learning situation, we inherently use our previously learned knowledge. So for example, if you wanted to pick up a new programming language like Python, familiarity with other programming languages like Java and C++ can help you to pick this new language much faster and in a more efficient way. Similarly, if you know how to play ping pong, if you and you wanted to learn a new sport like tennis, you can learn it much faster. So inspired by human ability to transfer knowledge, machine learning community has also focused on transferring knowledge as a way to overcome the cold start problem. And here, our aim basically is to improve the performance for one customer as target with having access to enormous amount of available data or models from other customers, which we refer to as source. But how can we do it more specifically? So as Franziska mentioned, the cold start problem is usually caused by different types of shifts: input shift, output shift, and conditional shift. And if you're really lucky, you're just facing one of these types of shift in your problem. But in most real-world scenarios, often we face all of these three types of shifts together at the same time, which is like really sad and scary at the same time. But if you're in a situation like that, don't worry at all. You're in our shoes, and we'll let you know how we managed to at least solve it to some extent. So I'll first start with addressing the input shift. There has been a lot of different methods in basically a research area called instance-based transfer learning methods. The methods or approaches proposed in this area focus on re-weighting the source instances in an attempt to address this input shift. Or to put it in a simpler form and explain it a bit more simply, is that if you have a bunch of samples from your target domain or your new customer, and you have a lot of samples from your previous and old customers, which we refer to as source samples, an easy way is to use the previous data or knowledge is that you can train a binary classifier that tries to distinguish these two groups of samples. And then based on how close your source samples are to the decision boundary of your binary classifier, you can weight them and see how close, how similar they are to the new domain. Or to put it in the context of, for example, Tractable, if they have a bunch of samples from US, and US cars are more like SUV, and we have access to thousands of samples or images from other types of car in the world, we can train this classifier to tell for each image how similar it is to US cars, and basically use these weights to directly use these weights to train a new classifier for for example, US customer. Another group of techniques that can be used to address the input shift are called feature-based transfer learning methods. And these are the techniques that have become really popular in the past couple of years. You have seen a lot of new and different architectures of neural networks that try to fuse the information and like features from different domains into a lower dimensional space. So these methods generally work by mapping the features from both domains here, target and source, into a lower dimensional space while keeping the predictive features and reducing the dimensionality. And by doing this, they also address the differences between the input distribution or input shift, to put it that way. So yeah, and there has been a lot of other techniques, and especially on deep models. But in the past few years, I think there has been a lot of focus on input shift, but we haven't seen that much focus on other types of shifts, which are output and conditional shifts, which from my opinion, happen even more frequently in real world scenarios when you're dealing with different types of data. And one very popular technique that have kind of become a standard in the past few years to deal with output and conditional shifts are basically fine-tuning neural networks, which is one method that lies in a bigger bucket of parameter-based transfer learning methods. So what we have seen in the past few years is that if you're facing conditional shift, you can pick a model that's been trained before and tune different parts of this model that are responsible for different things. Like the first few layers are usually responsible for producing meaningful representation, and the last few layers are usually responsible for the classification task. So people usually tune different parts of the network to address different types of the shifts. And it's been seen that like this method has received a lot of, has shown a lot of promising results and kind of is the standard. There are more and fancier methods to address output and conditional shifts in the context of deep models. But I think at least if you're working on a real world data set, I highly recommend always starting with the simplest methods, things like this, and then, seeing if you need to get into more fancy version of these methods. And in addition to this, there is another sort of techniques that is similar to transfer learning, but slightly different, and which is called ensemble learning. So in ensemble learning, the idea is that if we have access to many, many different models that are trained before, can we make a better model out of all of by combining and aggregating all of these models? Can we make a strong model for a new customer? And the idea or analogy behind this is that if we have different experts in a room, we have coming from different corners of the board and with different expertise, can we combine the knowledge of all of these experts to make an Einstein? And the answer seems to be yes. So we have seen a lot of promising results by ensembling techniques in the past few years, especially from Kaggle competitions. So now the question is that how do we put all of these techniques into the context of Tractable? So as Franziska mentioned before, in Tractable, we started by having a few images from a damaged car by some metadata. These images are then passed to the AI pipeline, which contains two different components to produce the repair estimates. So as a worldwide AI industry expert, Tractable has access to more than 300 million images of different types of cars around the world with every possible types of damage. And having access to that huge data set allows Tractable to create a visual damage assessment module. And this module basically can create an abstract domain independent representation of the car. So this representation is basically contains all types of information that we need for the domain adaptation part. So having access to this representation, what we build is what we build is basically a domain adaptable layer. And this layer basically adapt the repair methodology for each new geography. So in this layer, by having access to the information and representation extracted in the visual damage assessment module, we basically can adapt to new geographies very quickly by using the techniques that I explained in the previous slide. And yeah, so having said that, we kind of managed to make a lot of improvement, at least in this case, and solve the cold start problem to a good extent. But now, having said that, I'll pass it to Franziska to talk about the outcome of solving the cold start problem on the business side and how it can help other AI startups like Tractable.
Cool, thank you, Azin. Yeah, so the impact of solving this is enormous in Tractable. So now we can expand to new markets quickly and efficiently. So no need to collect huge amounts of data, no need for very long, lengthy model retraining, no need for months and months of research development work. We have managed to get for new customers a 20% plus performance gain over these non-adapted models. And that's what really takes you from a kind of, oh, the AI is okay, but it's not really that good, to, oh, wow, this AI is like better than humans and is bringing us value because of its high accuracy and the fact that it can make these decisions so quickly, which is amazing. Secondly, we've reduced costs for labeling and data capture. This is probably like the most remarkable one for me, is that we can now make expert level AI. Oh, I think my my slides have packed in. Let me see if I can bring them back. Okay, Fine, it's back. It's back now. Anyway, as I was saying, we can now make expert level AI with 10 times less data than we needed before, which is great because now we don't need to spend a lot of time labeling. We don't need to invest time for data capture as much as we did before. Next, we have faster customer onboarding and earlier revenue recognition. So from the point of first talking to the customer to actually live processing their auto insurance claims has reduced by 25%, or kind of even over 25%. And this kind of, it seems like a small number, but actually if you're scaling your business globally, this makes an enormous financial difference to how quickly you can move into new territories and conquer whole new markets. And finally, is this differentiation and brand elevation. We can go to a new customer in some random country all on the other side of the world where our AI hasn't seen their data before, and we can actually do a pretty good job. And they say, wow, your AI is able to perform as well as our experts, even though it has had relatively little new training. And that makes us best in class for AI worldwide on this task. And this is what has really allowed Tractable to grow so rapidly in recent years and brought us all across the world. And right now we are actually processing more than 500,000 claims every single year. That's over 500,000 people whose lives we make better by speeding up their accident recovery process, which is great. And it's actually a lot more impactful than the random physics that I was doing before. So I think it's really sweet. I just want to leave you with a final statistic that I found in Forbes recently, that 40% of European AI startups don't actually use AI as part of their business. Issues like the cold start problem is what's stopping companies scaling and actually using AI. And the fact that we've managed to solve this with the help of the Georgian team means Tractable is not one of those startups, which is amazing. And so if you're interested in this, thank you for listening and come work for us because it's great.
Amazing. Thank you, Franziska. Yeah. So I also wanted to add, one last point. So we also have a forum, open forum for people, coming from the growth stage AI startup that join us and share about the problems, challenges, and the solutions that have found to be working for them. If you also wanted to join our forum, please feel free to send us a message on LinkedIn, and we'd love to have you there.
Okay, fantastic presentation. I really enjoyed it. I guess I'll give a round of applause for everyone. So now for some questions. Okay, so one from the audience. With the upcoming kind of the emergence of autonomous vehicles, like Google is starting to test, I think, road taxis, or is moving beyond testing and actually deploying it. How does Tractable see the future of kind of claims with this kind of automated self-driving kind of insurance claims?
Yeah, that's a very good question. So in the future, when there are more self-driving cars, they will likely be safer. So there will be fewer of these kind of one car is just driven into the side of the other car types of accidents. But actually, the decrease in number of accidents due to self-driving cars will actually be offset with the increase in number of auto insurance claims due to like global warming. So it's not so much that kind of business will go down, it's rather the nature of damage is going to change. There are going to be more like flood claims, more hail claims, and a lot more lighter damage claims, as there are, I guess, kind of large collisions. So this is something that Tractable is actively working on right now, is how do we kind of scale and adapt to that changing.
Right, so in terms of your, are you saying you would see like the type of data would shift from maybe camera, kind of phone camera type data, now it's satellite imagery where you're looking at flood zones, or you're kind of trying to, like, in terms of the, when you're saying disaster damage, this is what you're talking about, right? Like this kind of
Yeah, so it's not necessarily a shift from like phones to satellites, but rather a shift from kind of a huge dent in the side of a car to many small dents on the top of a car. So it will still be a sort of an input shift, but it will be on the.
So this is still car related. It's always, this is kind of automotive kind of claims. I see. Okay. I guess in terms of one thing that wasn't kind of, maybe you can kind of expand on is what is visually shifting when you're moving between different geographies? So when you're trying to adapt, let's say, to countries in Africa, and like the types of cars, let's say if the type of the car is the same, so if you have, let's say, Hyundai or Toyota cars everywhere, what is actually causing the domain shift that you have to kind of address?
So very frequently it is because the cars are different. So the kind of pickup trucks that are very common in the US, you hardly see them in the UK. And also the sort of box cars you see in Japan, very rarely see in Europe, very rarely see it in the US. So that is one big problem. Another thing is just the way that people take photos. So different countries have different standards for taking photos of the car, and the experts are able to work with different quality, different levels of, I guess, completeness of the photo set. And so we need to be able to kind of adapt to all possible conditions that people
right. So it's more a matter of kind of the user, training the user, and it's like there's either you on the machine learning side, you make it more adaptable to kind of this variance in pose, variance in kind of imaging style, or you could try to maybe train the user and say this is kind of like this is the process that you would take. You would need to in order to kind of like take the photos for the algorithm to kind of produce this assessment. Like for example, like fingerprints on Apple, it'll kind of, in order to calibrate, it'll ask you kind of to sample several times and kind of visually give this to you. So how do you, I guess, how do you address?
Yeah, so I think, there's very much the visual shift, different kinds of car, different conditions, but we do also, in the kind of video we showed about app, we do provide feedback to the users about the quality of the photos they're taking. If, for example, say they've had a frontal collision and there are no photos of the front of the car, that seems pretty strange. So we'll ask them to either take more or to take better photos. And we provide them as well with guidance to hopefully a bit of control over what sort of input you get. But no matter how much guidance you get, you still get a huge range of different things. And so it's super important to maintain like a strong
certainly. I guess there's two questions that kind of arise from that. Let's say, can you use something like, why not look at the 3D structure if it's something like you can do kind of 3D reconstruction and you're having a person take photos from kind of different points of view. And so now you're kind of the 3D structure is a little bit more invariant than, let's say, a set of images. And so now you have a 3D structure, which is kind of tracking the morphology of the damage. So I guess in terms of kind of, why not like a more invariant kind of data structure like that?
Yeah, I think that's a very good question. I think even though we try as much as possible to have control over the photos that our users take, one of the difficult things is it's often just not very good to take, or not very easy to take these good photos. Like if you're out at night, then you probably can't get kind of nice, clear pictures of the damage. And also, if you're, say, parked in a parking space, you can't really walk around the car in a full 360 to get all of the angles that you need because there are kind of cars on the other side. So what we found from talking to our users is kind of trying to take maybe 4 to kind of 8 photos is sort of reasonable. Asking anything more, then it becomes a very kind of frictionful process, I guess, and the users end up saying, oh, this isn't worth it, I'd rather just have a human come and do this for me. So it's always, I guess, that balance between making it easy for the users and also collecting
I guess in terms of the damage assessment, that's kind of you're kind of separating the two steps, right? One is just pure detection without any kind of costs, let's say associated. You're not predicting the cost necessarily directly. You're just you want to based on the car, the damage and the car together produce kind of a more produce a cost estimate. Is that kind of how the process goes?
Yeah, it's very much the first stage is kind of what is the damage across the car, and then the second stage is what do we need to do to repair this in this country.
I guess one question that kind of comes to mind is how do you differentiate between fraud, let's say, or like let's say like an inspector who comes in and investigates a scene of an accident. They have a lot more context, a lot more cues in order to kind of detect like let's say a narrative, like a kind of a coherent narrative for what the accident was, right? But a computer vision algorithm wouldn't be able to kind of pick up on some of these nuances, maybe if there was fraud involved. So like, how would you kind of deal with that, especially in some countries? Maybe I'm stereotyping based on kind of social media kind of thing, but like let's say Russia or like Middle East, there's a lot of automotive kind of fraud, let's say, right? Like how do you, if you're expanding into these markets, how do you deal with those kind of things? Yeah.
Yeah, I think everywhere around the world has fraud, but different countries have different kinds of fraud. So there is the type where there is maybe damage that is not related to the accident, that people are like, oh yeah, just kind of clean that damage up as well. So that is something our models need to be able to pick up. So our model needs to be able to say, hey, that's super rusty, so you can't just claim for that. So we need to be able to pick up these fraudulent cases. And there are other things where people say, oh, I just left my car in the car park and then I've come back and someone's driven into it, but they quite clearly have like a pole in the back of their car, like a pole-shaped dent. And so we call this like a flying pole problem. So we also need to be robust to these sorts of things. Now, obviously, that is a much harder thing to do because it's not just, I guess, a visual assessment. It's basically you've got to do visual and NLP at the same time to understand the description and cross-reference that with the images. So that is a lot trickier. That is an active area of research for us right now, and how we can.
I see. I guess maybe a question for both of you, Azin, if you also want to kind of participate, but how do you measure the accuracy of the kind of detector itself? Like, how do you, is it just kind of segmentation and you're looking at predicting, let's say, distant like surface normals or something? How does it actually, how do you assess the kind of prediction accuracy?
Yeah, I think for different customers, for different use cases, the thing that we want to optimize for is different. So we have a use case right now with our estimate is used to decide whether a car should be a total loss or not, whether you should just like scrap it or whether it's worth repairing. So actually there, the important metric is that total estimate cost, and that needs to be accurate so we can make an accurate kind of trade-off between that and the car's valuation. So for that case, we would kind of optimize our AI components to make the best total cost. In other cases, for example, if we're trying to detect fraud, it's very important to, I guess, have high precision there. So if you're calling fraud in some countries, that can kind of go to court. So you've got to be really sure that you're right in what you're doing. So for those cases, just this classification of fraud or not needs to be super precise. So it's very dependent, I think, on your use.
Right. So I guess how do you see? But let's say you can weight the how you measure the accuracy kind of depending on the cost in a certain sense, right? Like let's say if it was a Mercedes that got damaged, if you make a mistake in terms of estimating for that, it's a lot costlier than let's say if it was like a sedan, some kind of Toyota, whatever it is, right? So how do you how do you deal with outlier cases that might actually be very expensive if you make mistakes, or how do you deal with those kind of instances?
Yeah, I think that's a very important point, because if, for example, you have a crash in a Lamborghini, our AI will have seen very few Lamborghinis and probably won't be able to do a very good job of kind of accurately determining the price there. So with all of our AI, we have kind of some measure of certainty. And so if you have a crash with the Lamborghini, we don't know if it's totaled or not. And then we'll say to the insurer, kind of, we think it's this, but we're not sure. And so we always do kind of measure the certainty and know, for example, if there is a lot of say internal damage to the car, you can kind of see it from the outside, but it's very difficult to tell actually how much internal damage there is because it's kind of inside, you can't see it, you've got to take the car apart. Then we will tell the insurer that we're working with, this seems to have a lot of stuff that is within the scope of what the AI can do. So you should take a look at yourself. But this does happen on a relatively.
I see. So it's kind of like looking at the confidence of the model, hoping that it's kind of well tuned, and then going from there, right? And do you see kind of adversarial data points? Is there kind of like, what are some instance examples of like something that will throw off the model that requires this kind of sorry.
Yeah, so I think let me think what a good adversarial data point. So actually, one problem that we did have to deal with at some point is often if there's a small amount of damage, then you might want to kind of draw a circle around it or point to it or kind of make some indication. Or if you have like a small damage, you want to take a close up of it. So when we first trained the AI, we found that actually it seemed to pick up on these visual cues quite well, which was obviously not very good because that leaves us open to fraud. So it's about kind of identifying these biases. So the way we do this, we have a team of in-house motor engineer experts, and they can tell us like, oh, people always point if there's this sort of damage or whatever. So we can say, okay, let's look for some good data points so that we can become robust to that. Like, how can we collect more data related to those biases, and then make our AI so that it doesn't fall for these tricks anymore.
Right, and I guess in terms of like papers for overcoming kind of cold start problem, and maybe in the literature itself, let's say in NLP, there's pre-training is the standard now with transformers, and you're doing kind of this unsupervised, let's say, or self-supervised, let's say, pre-training, and that seems to transfer very well. Let's say in the case of GPT-3 in terms of like meta learning and being able to kind of generalize to a lot of tasks that weren't necessarily in the data set, let's say. So like pre-training seems to be very successful in NLP, and then now you're starting to see kind of image GPT and pre-training gaining kind of, and doing transfer learning is also gaining kind of some significance, or some is kind of being increasingly used in the computer vision space. So I guess have you also looked at kind of just general pre-training on lots of data, kind of unsupervised way, and then fine-tuning with kind of your data set?
So Ali, maybe I want to add a comment on this about your previous question too. So the way we were kind of like thinking about this problem is we decoupled it into two steps. The one that is about extracting meaningful features, and the last one is about like repair methodology. So in our case, it's, you know, the methods that you were kind of referring to are great like methods if you generally wanted to get into a new geography. But in the case of Tractable, in the last layer, which is like the repair methodology, that can be quite different when you move from geography to geography. So even assuming that we can have very meaningful representations, or, you know, embeddings or images by using methods like GP3 or models like GP3, it still doesn't solve the second step of the problem. It would kind of like feed nicely into the first step, which Tractables are currently like doing a great job in, like, you know, generating representative and meaningful representations for the damage. But then it doesn't address the second step, which we're kind of like trying to address.
I see. I guess in terms of kind of the architecture that you're kind of performing transfer, it seems like you're taking the last layer, you're kind of you're freezing the weights for the previous layers, and then you're just kind of fine tuning based on the last layer based on geography. I guess how this is kind of like what do you see in terms of like why limit how you perform the fine tuning in terms of like the architecture? Why let's say if you have the compute, you have the data, why not just fine tune? Like let's say with transformer models, you're usually still training the entire model, right? So I guess what is the advantages that you've seen with kind of the approach?
I can add one comment and then pass it to Franziska to elaborate. So one thing about this is that usually you still need a reasonable amount of data, which is definitely not the case when you're onboarding a new customer. So that's the first problem. So they don't necessarily help you to address cold start. They kind of address the warm start problem, I would say, and change it to a hot start problem. So that's one thing, and also related to your previous question about. Sorry, I forgot the previous point. So Franziska, do you want to add on this as well, and the visual, like and maybe also to add another comment for Franziska. We don't necessarily do the fine tuning. It's like the techniques that we apply are a collection of, a bunch of like different techniques to address those types of shifts. And the solution that we found to be working is, a collection of those techniques being applied on top of the
so it's kind of like ensembling and you're kind of adding to this ensemble features that would help kind of prediction.
Yeah, with a lot of like different details. It has a lot of deep details, and probably we won't like have the time to elaborate more on it and more deeply in this session. But it's like a combination of different techniques that is applied on top of the models.
Okay, great. I guess one or two more questions then. I guess in terms of the research approach, going from research and then applying that in practice in kind of both of your experience, you just kind of base it on papers that you read. You look at let's say some recent papers that address this issue, and then you try to adapt that to your problem, or are you just kind of is it very maybe it's kind of from Kaggle experience, you just know how to kind of work with this problem. So what is the kind of the methodology in terms of kind of doing this?
Yeah, so I guess kind of whenever Tractable builds an AI, what we want to do is emulate the kind of expert's thought process using the AI. So actually the first step is usually talking to our in-house experts and understanding how they make their decisions. Kind of, are they purely visual? Do they use text? Are there any other features? And kind of from the images, what things do they look for? And how do they, I guess, select the right sort of visual input in order to make the decision? And kind of once we've kind of worked out how the human does it, we kind of go into the literature and see what techniques sort of approximate that process. And it often means kind of taking deep learning techniques that have worked well in academia, slightly kind of tweaking them and adapting them for our data and kind of the input that we have, and then trying to train an AI model from there.
Okay. Yeah, let's see, one more question then. I guess where do you see the future of kind of the domain adaptation and working in cold start problem in terms of like both tractable and maybe more broadly? What kind of techniques are you seeing that would be something that's kind of would become more prominent, let's say, in a year from now, et cetera?
So at least on the visual, as you mentioned, there has been a lot of breakthroughs in the past few years for like the NLP. And the first thing that we're kind of like hoping to see is that the idea of self-supervised learning and models like GPT-3 getting into the visual domain too. So that's definitely one thing that we're kind of expecting, and that would help to solve the cold start problem to some extent. But at the same time, I feel like there has been a lot of research going into things like zero-shot learning, So I think in the next few years, we're kind of like expecting to see strong models like GPT-3 coming into the visual domain, and at the same time, seeing more sort of techniques address types of shifts that we covered in the data, hopefully. But including all of these, I still believe that anytime we talk about the cold start problem, there is still a lot of value in using classical methods in addition to, as well as the new techniques, and because they all have different advantages. And I think what can be really promising is if we make a collection of these techniques, classical techniques plus the new techniques that can work quite well together. And really looking forward to having a solution that can be a remedy for all cold start problems, not just tractables.
Certainly. Well, I mean, I've learned a lot during this presentation. I'm very excited to keep tracking your research and work of Tractable AI. Some people in the chat are also curious about maybe some papers that helped that you kind of that you could share that kind of address these issues. Maybe from a kind of a practitioner point of view, it'd be very useful for people, kind of remaining audience members. Otherwise, thank you very much. And I guess if you want to end on any kind of note, please take it away. Thank you.
Cool. I guess, yeah, thank you very much. And thank you everyone for joining us.
Yeah, thank you, Ali, for moderating the session. And thank you so much, everyone, for joining us today. Have a wonderful rest of the day.